Hi everyone, thank you for attending this talk. I'm Caesnan Leditto, I'm from Monash. So this work is joint work of Monash, CSRO, and SUTD. So today I will be presenting my work on quantum algorithm for ranking data on higher order networks. So let me briefly state our motivation of this work. So originally we want to solve problem that lies in this area. And we realized that recently there are many quantum algorithms for topological data analysis. Checks out all these three ingredients. Importantly, that this algorithm achieve potential polynomial to superpolynomial speedup, and it is robust against the quantization method so far. But in network science application, this type of algorithm has limited applicability. So it only counts the number of holes. But in certain cases, this is still useful for network science problem. So our goal is to broaden the application of QTML in terms of network science applications. And in particular, we construct a new algorithm based on quantum topological data analysis tool and to rank data on higher order networks. So we also want to still maintain the similar quantum speedup that is shown in the QTML. All right, so let me set up the problem. So we have a group of voters and set of alternatives. And the voters are asked to compare between two alternatives. And by comparing, I mean give preference value between each pair. So this is called pairwise comparison data. But in general modern data set, the data can be incomplete. It means their pairs are not compared. And the number of voters that vote each pair are not the same. So with this pairwise comparison data set, we can generate a graph or simply shell compact if you like. So in this case, all alternatives are nodes in the graph, and preference between two alternatives are edges. And preference values, we put preference values on the edges of this graph. So statistical ranking problem is given this input data, we want to output global ranking of alternatives. And this is in general a hard problem because we have this cycle of alternatives and this is called inconsistency. So the voters cannot decide which alternative is better compared to others. Solving this problem is an NP-hard problem. So exactly, solving this problem exactly is an NP-hard problem. So the idea of HodgeRank is to solve the problem approximately. So using the discrete exterior calculus method, HodgeRank output the scores of each alternative. So if we apply the first boundary metric, the transpose of the first boundary metric of this simply shell complex, we output the new assignment for each pair. And this assignment is just the difference between the two alternatives. And importantly, that this solution, these scores, satisfy this L2 minimization problem, indicating that we suppress the inconsistency that appeared in this pairwise, this graph or this network. And we can measure the quality of this suppression using this quantity called consistency measure. So finally, we can just sort these scores from smallest to largest, and we can get a globally consistent ranking with consistency arching. Okay, so the K-HodgeRank is generalization of HodgeRank. So instead of putting data on edges, we put the data on simplices. This type of network is called higher order network, and it has been studied extensively in the last 5 years in the computer science community, network science community. And this has been useful for analyzing complex system that has pairwise, beyond pairwise interaction. For example, in brain or in collaboration network, and in many type of networks. So, HodgeRank, given data on K simplices, for example, for K equals 2, which is just triangles, will output the data on edges. And if we apply the transpose of the second boundary matrix, we'll have a new assignment for the data on triangles. And this also satisfies this minimization problem. Okay, so for the general K, given data on K simplices, the HodgeRank will output data on K minus 1 simplices and satisfy this minimization problem with this consistency measure. Okay, so this is the idea of HodgeRank problem. BK is the K boundary matrix. Okay, so the algorithm, the quantum HodgeRank, is the quantization of the HodgeRank. So given the data, the input data, encoded in this quantum state, in the amplitude of the quantum state, we use projected unitary encoding of the boundary matrix and QSVD to approximate the projection to the solution of HodgeRank. So the solution now is in quantum state. Okay, this projection, the cost of implementing this projection on quantum computers scales quadratically in the number of vertices and quadratically in the condition number of the boundary matrix. So n is the number of vertices, kappa is the condition number, and epsilon is the precision. Okay, classically, implementing this projection, we can measure in terms of arithmetic operation in the sparse linear solver. And this is scales linearly in the number of K simplices. And this is much, much higher compared to the number of vertices. Okay, so why we use this classical baseline? Because in the recent paper, there is a classical hardness problem of solving the second HodgeRank from solving sparse linear equation. So it says that solving the second HodgeRank is as hard as solving sparse linear equation. So by assumption that solving HodgeRank is as hard as solving second HodgeRank, we can establish the classical hardness of a HodgeRank problem. Okay, so for superpolynomial advantage regime, we consider the instant that is given in the quantum topological data analysis paper. So this is a complete multipartite graph, and we analyze the complexity, the cost of outputting consistency measure classically and quantumly, and we have superpolynomial cost separation if the dimension of simplex is logarithmic in n. So we have caveats that the state preparation is easy, is efficient. So in general, this is not true for higher order network data. But in our upcoming paper, we show that there is data that is given data on the nodes. We can aggregate, higher order data, aggregate data from nodes. This is called higher order node aggregate data. And we can prepare the quantum state efficiently using this type of data. So this is efficient state preparation for quantum HodgeRank. And as future work, we are also interested in solving standard HodgeRank with exponentially many alternatives. If we use quantum HodgeRank to solve this problem directly, this is also exponential cost for quantum HodgeRank. So we find an instant that if this standard HodgeRank graph lives in the primal complex of the simplicial complex, then we can exponentially reduce the cost of solving this problem. And also as feature work, we want to establish the hardness of quantum HodgeRank. So the idea is to quantize the hardness gadget from the classical one, the one that I showed before. So the idea is we take input from QLSP, and this will, using the hardness gadget, we can encode this equation into intersection of triangles. And then this will construct the second boundary operator. We can solve it using K-HodgeRank problem. So this will reduce the QLSP problem, QLSP to quantum K-HodgeRank problem. And as you know that QLSP is PQP complete, and we are hoping that it will give us complexity theoretic justification for K-HodgeRank problem. Okay, so beyond ranking, this algorithm can be also useful for what people call Hodge decomposition, and this is useful for many applications. For example, probing the phase locking in the couple phase oscillator, or quantifying the curveness in the protein folding, solving the boundary value problem, or analyzing Nash equilibria in continuous scale. Okay, as a summary, statistical rank problem can be represented as a graph, and HodgeRank can solve this problem approximately. We can extend this idea to higher order network data. Implementing this K-HodgeRank in quantum computer is way, way cheaper compared to the implementing it in classical computer. And we also show that we have superpolynomial advantage if we consider this type of instance. So I would like to thank my collaborator from Monash, CS0, Data 61, and SUPD.